as promised, we have an example here that shows the maximum covering location problem. This is a little bit larger problem than the one that I shown before, okay? And I would like to explain you how I came up with this problem. So we do have a few facilities, right? Those again could be things like post office and so on. And those are in green, okay, at different coordinates. I will provide the coordinates separately. So they are A, B, C, D, E, F, G, H, okay? And then we also have around these facilities a radius, okay, a radius of a value of 1.5, okay? You can see the X and the Y axis and how they are ticks along those axes. Second thing, we do have demand nodes. They are in red, okay? Number 2 here, number 3, number 4, 5, 6, 7, 8, 9, and 10. And so those, again, these demand nodes could be the centroid, for instance, of a geographic unit. Okay? It could also be individual, but in this case, I'm going to use some sort of aggregated population value. Okay? And that value, that weight, if you want, is J sub I, and in this case for the first one, so that would be J sub 1, and that's equal to 23. Okay. For the second one, that's 54, sorry, that's 25, for the third one, it's 54, and so on and so forth. And so we can see which demand node, right, are more important than others. The one that I believe is the most important is this one here, 4, that has a demand of 74. So when I look at this problem, and if I could only, let's say, use or open one facility, it may well be around this area here because there is a really high demand. But that is where the CPLEX is very interesting than just looking for, okay, where it might be the highest value, right? So it's important. So this is sort of the setup. So the first thing that you actually need to find out, right, is for each demand node, which facilities can cover that demand node. And that will be reflected in the constraints. So now, let's look at the objective function and how we work this out. We have a maximization problem. We're trying to maximize the demand that can be covered. Remember, Y sub I is equal to 1 if that demand node is covered, right? And we do this for each of these demand nodes. There are 10 of them, and the coefficient that is before is the demand. Subject to, now, for each of these demand nodes, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, we are going to see whether or not there is a facility that can cover the demand node. And I just wanted to show you for number 1, I wrote it down, but normally you will not see it, okay? I put 0 here is greater or equal to 1, because we cannot find any facility that can cover. Let's look at the second one. So where is 2? 2 is here. Now, if I look at 2, which facility can cover 2? That would be only H. So you have XH greater or equal to Y2. How to interpret this? If Y2 is covered, then XH must be open. You cannot cover Y2 in a different manner, okay? Let's look at number 3. 3 is here. 3 can be covered by both H and F, okay? So then that's why you have XH plus XF greater or equal to Y3. How to interpret this one? If Y3 is equal to 1, that means that that demand node is covered, and that means that at least either XH or XF must be equal to 1. Both could be open, that's fine, but at least one of them should be open. And if that's the case, then that demand node 3 is covered, and you can do this for the rest. What are the other constraints? So one of them here is the fact that we can only open one facility, so you do XA plus XB plus and so on, is less or equal than P. P could be, in my case, equal to 1, right? So that's kind of the budget constraint. Then we have this integer constraint right here. So that's kind of the setup. Now, very interestingly is that I can tell you right off the bat that if P is equal to 1, okay, then most likely we're going to use either H, because it can cover two demand nodes here, or F can cover 2, but we will have to see what the population is. Okay. So then we'll see, okay, what happens if P is equal to 2, what happens if P is equal to 3, P is equal to 4, and so on and so forth. And interestingly enough, I would like also to see what would happen if, you know, and I don't know if I will be able to do it, but what would happen if, let's say, this this particular demand node that's currently equal to 33 is all of a sudden equal to 133, for instance, then it's not going to be F that we're going to choose, but maybe it's going to be J that we're going to choose because the demand node is so high there. Okay, so we are going now to solve this in CPLEX and see what happens. All right, briefly here, I just want to show you before CPLEX in GIS how this works. So I have in this Excel file here the facilities A through H with the coordinates, okay? And then I also have the demand nodes here, 1 through 10, with the coordinates X, Y, and also Z, which represent the demand. So then those files are then saved as text delimited, text tab, or CSV, however you want, or even in Excel. And then here, so I have this file. So here is one is, for instance, facility here, right? I can open it. Here you can open and you would see the X and the Y's, for instance, actually X, Y, and ID, sorry, this was the wrong one. And then from here, you can do display X, Y data, then you would specify what the X field and Y fields are, okay? And I do that for the demand node as well. And as you can see, this is the same problem that I have on the blackboard. And I also draw the 1.5 radius around these facilities that appear in green, the radius in blue, and the demand nodes are in red. Now, let's see how we can use Python as well as the toolbox to generate this CPLEX file. So what I've done here, okay, is that I have a toolbox right here, a toolbox called MCLP Fall 2020, and inside I have a script, okay? I can open this script here, should be location, well, the problem here, but that's okay. And it asks me, it asks me here, what is my demand? My demand is right here, demand node, so I'll go and ask to add demand nodes, okay? You already will receive this shapefile, so no worries. What is my population field? That's Z. Now remember Z here is this one, right? Right here. What is the coverage? Those are going to be the facilities here. Output file, that's where my linear programming file will be saved. This is the default here. You may have to change if you don't have a temporary or if you use a USB, for instance. What is the coverage distance? Let's say 1.5. And the number of facilities I will say is equal to 1. When this is done, I run this here. And this is just going to generate the LP file, no problem here. And I can then navigate to the ctemp here, up quickly, and see my file out right here. And this will be my linear programming file that is already nicely set up. And you can see this is the same that I have on the blackboard, with the exception that I don't have on the blackboard this type of constraints here, but that's quite all right. And the integer constraint could also be binary. It's the same here. They will be binary no matter what. So that's it on the GIS side. Now let's move into the CPLEX side. All right, solving this file, this linear programming file in CPLEX right here. Again, this here I have, it's called out. I have CPLEX open. Say read. And I'll drag the file here. Again, it's easier. And I put LP because linear programming file. I optimize it. Okay, it tells me the objective is 128. Okay, and if I would like to know what the solution variables are, this one here, and it tells me that both demand node 3 and 4 are covered with or by the facility F, okay, objective function 128. Now, let's keep that in mind for afterwards. And then, what if the number of facilities that we can open is equal to 2? So I change this in the text file. I can save it, Control S, or save here. And then here I can rerun the same. So you can use the up and down arrows here. So I up arrow, optimize it. The objective function is 167. By having 2 facilities, we can cover a larger amount of demand nodes. And I can see which demand nodes are covered. You have 3 and 4, and as well as 10. And the two facilities that are chosen are F and D.